Today I'm going to talk about our Enterprise-Centric Offloading System. And the reason that we're focused on this is because that we're seeing an increasing number of mobile devices being used in enterprise networks. Smartphones and tablets are becoming important platforms for users in these enterprises. And as they become more popular, these devices need to be able to run more complex applications that are either part of the business of the enterprise or just other supporting tools. The problem that we face is that these complex applications have significant resource demands that they place on these mobile devices, CPU and memory, and more importantly, energy of these resource-constrained devices. And so we need some way that we can reconcile the application demands with the limited resources that we have available on these devices. One way that we could do this is to specifically design applications to leverage remote services. So Google Voice Search, Apple Siri on the iPhone, Amazon Silk, which renders web pages in the cloud and then delivers them to the Kindle. These are all examples of applications that have been designed specifically to use a remote service. The problem with this approach is that we have to use this paradigm at the time we're developing the application. And we want something that's going to work with an application that I can just go and download off the Android market, regardless of how it's designed. Another approach that we could take would be to use something like remote desktop or VNC, where all the computation and the things that need a lot of resources are going to happen on a desktop or a server somewhere. The problem is that the user interface you'll be interacting with is designed for that desktop or server. It's not designed for your mobile device. So instead what we focus on is a third approach that's been widely proposed, and that's application-independent offloading. And the idea here is that we want to, at runtime, dynamically divide the execution of a mobile application between the mobile device and some compute resource that we have in the network. And the application code doesn't have to be modified in any way. We can take an application that's built to run on the mobile device and run this exact same code base on the compute resource for whatever subset of the code we want to execute remotely. And how we actually divide an application can either be informed by some sort of offline model or runtime monitoring of the application's performance. So several systems have been proposed that do this. Chroma relies on a tactics file, which has various ways that you could divide an execution between a mobile device and a cloud. Maui's focused on partitioning .NET applications that run on Windows mobile devices. And lastly, Clone Cloud is focused on Android devices, partitioning Java applications between a mobile device and a cloud. The issue is that there's several roadblocks for enterprises actually being able to adopt these offloading systems in order to reconcile the demands of mobile applications. The first of these is privacy and trust. Privacy is a paramount and very important concern in enterprise networks, and so we need to make sure that when we're offloading an application, we're ensuring the privacy of the data that that application is using. And existing systems don't pay attention to the privacy of that data when making their offloading decisions. The second issue that we face is that we need to be able to support many mobile devices and a diverse array of resources within a network. The existing systems assume that we're working with one device and that device is going to use a static dedicated resource, which just isn't practical in an enterprise network because resource capacity and availability is going to change, and also the devices and what resources they need are going to change over time. So our enterprise-centric offload system is focused on addressing these two roadblocks. And what we set out to do is to allow many devices to opportunistically leverage a diverse array of compute resources that may exist within an enterprise network. Public clouds, servers, idle desktops. We want to do so in a way that carefully takes into account where an application should offload its computation based on what we know about its privacy requirements, the performance and energy constraints that users or applications may have. And so we do this by augmenting the offloading decision process with resource considerations and privacy considerations. So I've talked about the benefits of offloading and the roadblocks that we have for enterprises to actually adopt this today. I'm going to talk about next how we address these issues of privacy and trust and resource sharing and churn. And then I'll end by talking briefly about our prototype and our evaluation that we did for a small enterprise setting using our prototype. So the issue that offloading introduces is that data may leave the confines of a mobile device without a user explicitly sending that data somewhere. The data is part of the execution state of an application, and so as soon as that execution state gets transferred to a remote resource, that data can potentially be compromised. And so in order to ensure sufficient privacy, we need to do two things. First of all, we need to make sure that the execution state is protected in transit if there's a risk that that data is going to get compromised as it's being sent across the network. The second issue is that we only want to use compute resources that we sufficiently trust. We don't just want to pick any resource. For example, we may not want to use a public cloud resource if we're not sure if our data is going to be compromised. The challenge that we face in ensuring this sufficient privacy is that we want to make sure that the benefits that we receive from offloading, as well as the opportunities we have to do so, aren't significantly diminished by the fact that we're potentially adding overhead by using these privacy requirements, or by addressing these privacy requirements. And so, as a good example of why this is really challenging, we look at what's the overhead of actually sending the data encrypted across the network instead of just sending the execution state unencrypted. And we see that in terms of how long it takes for the same amount of state, it takes almost twice as long if we're sending data encrypted using SSL or TSL, or TLS, excuse me. And likewise with energy, we also see about a 1.5 times increase in energy usage. And so we want to think really carefully about whether or not we actually need to apply encryption whenever we're offloading. Likewise, if we're limiting the number of resources that we trust, there's a possibility that we may not have a sufficient number of trusted resources available. And this may result in reduced opportunities for offloading. So the way that we address these concerns and make sure that we preserve the benefits and opportunities by minimizing the overhead is to take a data-driven approach to which privacy protection mechanisms we need to employ. The simplest, of course, is applications that are working with data that doesn't have any privacy restrictions. In this case, we can use any resources within the enterprise, be it a desktop, a server, a cloud somewhere, and we're not concerned with protecting the communication between the mobile device and the offloading resource. The second level of data privacy is data that's enterprise private. So here our concern is that this data is not accessible to users outside of the enterprise. So maybe there's some sort of internal memo that an application is working with. And so here we're only going to use resources that are internal to the enterprise. But since anyone within the enterprise can have access to it, we're not concerned about providing any protection on that communication because we're merely communicating within that enterprise network. The strictest level of privacy that we may have is user privacy. And in this case, we're dealing with an application where its data should only be accessed by a specific set of users. So payroll information is a good example here. We only want people in the payroll department to have access to it. And so we're going to limit which resources we use to a select set of servers and desktops within the enterprise. And we're always going to encrypt this communication across the enterprise network. So how we actually identify what the privacy protection is we have a policy file that statically specifies which label should apply for specific devices and for specific applications based on the types of data we expect that application to work with. So now let me talk about how we address the second issue that I raised, which is resource sharing and changes in the availability of resources. As I mentioned earlier, existing systems consider one device and they assume that there is a static dedicated resource that can provide compute resources for execution. What we actually want to be able to do, though, is to have many mobile devices opportunistically leverage whatever resources are available in the network. And there's several challenges that we face in doing so. The first issue that we run into is that devices are going to be running a variety of different applications that may want to offload, and they're going to have varying objectives in terms of why the user actually wants to offload this application. Second of all, we have a limited amount of resources in our network. Although we may have lots of desktops and servers, there's also lots of mobile devices, and the number of mobile devices is increasing. And so we expect that there's not always going to be enough resources to serve all these devices, especially if these resources have changing availability and very diverse capabilities in their processing capacity. And lastly, we don't know ahead of time when a mobile device is going to want to offload. And so we need to make our resource assignment decisions only based on our current knowledge of which applications are offloading. So the way that we address this in ECOS is that we want to multiplex applications onto compute resources based on the objective that the user has set forth. So we look at two different objectives. One is an application that wants performance improvement. And the idea here is that we want to make sure that whatever part of the application we're offloading, it should run faster on our compute resource than it would have if we would have ran it on our mobile device. And So here we pick resources that have an unused CPU capacity that's greater than the CPU capacity of the mobile device. The other objective that we may have is a device that wants to save energy. Here we're not necessarily concerned with how fast it executes. What we want to make sure is that it executes on a compute resource instead of executing on a mobile device. And so we can pick any resource regardless of its CPU capacity for these energy-seeking offloads. But since we don't want to negatively impact offloads that are seeking performance improvement, we make sure that we don't use those same resources. So we group energy-saving offloads together, and we group performance improvement offloads together based on what resources we have available. The second thing that we also want to consider is in assigning resources is affinity, or whether or not we should use the same resource for subsequent offloads of the same application from the same device. The benefit of this is that now we can cache execution state on the compute resource. So the next time that that application decides to offload, we have less execution state to transfer, which is going to cut down on our latency overhead and our energy overhead. And this is going to be especially important for connections which we need to have encryption, because that's going to increase that latency overhead. So by reducing execution state, we can sort of balance what we pay for that encryption. The downside is that this assumes that we have constant resources being available and a constant capacity on those resources, which just isn't true in most cases. And so when a resource isn't capable of handling a subsequent offload, or when it's no longer available, we have a couple different options of how to proceed. One is that we could deny offloads from the mobile device until the capacity of that device or that compute resource increases. So if a user comes back and starts using their desktop, we could say, all right, don't offload here until the user leaves again. An alternative option is that we could assign a new resource for that offload. The problem here is that now we're going to need to retransfer the entire execution state from the mobile device, or we're going to need to migrate the execution state from the old compute resource to the new one. And ECOS is flexible enough to use either of these policies. So let me touch briefly on our prototype and how we actually implement the privacy and resource assignment capabilities that I discussed. What we've done is we've taken the Android platform and modified the Dalvik runtime environment that runs applications on it to be able to pause execution of an application and serialize that state and send it across the network to a compute resource. And a compute resource is going to run a native x86 version of Android in a virtual machine. And again, it's going to run a Dalvik environment with that same set of modifications, such that now we can take and deserialize that execution state and resume the execution on the compute resource. The central component that's really important to the ECOS is this central controller that we have within the network. This is where the policy file resides that has the privacy labels. This is also where resources report their availability and their capacity to handle offloaded applications. So when a mobile device is running an application that has some compute-intensive component to it, for example, perhaps the AI component of a chess application, it's going to ask the controller if there's any resources that are sufficiently trusted that are also have sufficient capacity to handle this offload. And if a resource is available, we'll pause execution of the application on the mobile device and establish a connection to whatever compute resource the controller said we could use, optionally encrypting this connection depending on the privacy requirements. Then we'll go ahead and serialize the execution state and send it to the compute resource. Part of the execution will happen on the compute resource. We'll reintegrate any state that's changed back into the mobile device, and now we can resume the normal execution of the application on the mobile device. So to evaluate this, we considered a small enterprise setting where we had 12 phones. We emulated these phones using the Android emulator to a lack of enough actual hardware Android phones. And we consider that the enterprise is going to have 4 to 6 desktops that are a modern desktop, 2.4 gigahertz quad core, 4 gigabytes of RAM. We consider 2 different potential enterprise applications. One is something that's going to use AI decision making. We actually use chess as a stand-in for this here because we didn't have access to an actual AI decision making application for an enterprise. The other thing that we look at is speech to text. And so we look at doing multiple speech recognitions and see how can we help that using offloading. And we emulate the CPU and memory consumption of a speech-to-text application because the actual none of the existing open-source speech recognition applications provide source code that works with the libraries that are available on Android. We consider mobile devices that have varying objectives, either performance improvement or energy savings, and varying privacy levels. So here's the 12 phones shown on the bottom. You can see that phones 1 through 6 are running chess, and phones 7 through 12 are running our speech recognition. Phones 1 through 3 and 7 through 9 are seeking performance improvement, while the other 6 phones are seeking energy savings. So without offloading, in order to do multiple moves of the chess application or to do multiple speech recognitions, takes a significant amount of time. But if we make 4 desktops available to do offloading, then suddenly this total execution time for the application is significantly reduced. So in the case of the chess applications, we can potentially use any of the 4 desktops that are available. Since we have privacy constraints for the speech recognition application, only 2 of the desktops are trusted. And so those 6 phones need to only share those 2 desktops. And in this case, there's not necessarily always enough desktops to serve our applications. Phone 10 wasn't ever able to actually have resources that it could use, and so it didn't receive any benefit from offloading. It always had to run on the mobile device. But if we add more desktops that we can make available, now we can opportunistically leverage these additional resources, and now all of our devices are able to receive some benefits from offloading. So to summarize, our Enterprise-Centric Offloading System considers the privacy requirements and the costs of adding privacy mechanisms to preserve privacy. We consider which resources we should assign based on the goals that a user has, and we also seek to still maximize the latency and energy benefits by making resources assignment and privacy protection decisions carefully. In terms of future work, we want to look at how we can dynamically assign the privacy labels based on the current data an application is working with. We want to look at how we can automatically provision network paths in addition to compute resources. This means we'll be better equipped to handle both mobility of mobile devices, changes in compute resources, as well as provide higher bandwidth guarantees so that execution state can transfer even faster and we can lower that overhead that we're incurring to transfer that state. And lastly, we'd like to evaluate our system for a larger enterprise setting. So with that, I will wrap up and take any questions that you may have. No, so the applications themselves don't need to be modified. Because of the fact that we're running in a virtual runtime environment, the virtual runtime environment can see what the underlying structure of the application is. Yep.
So I'm curious, once you get to dynamic privacy label assignment and you're dealing with applications perhaps declassifying data, do you think you'll be able to keep the applications unmodified?
Yeah, so the hope is that because we can look at things at the sort of underneath the application, because we're dealing with a virtual runtime environment, we can see all the system calls and file accesses and network accesses that an application is going to make. And so if our system can understand that a certain network access is going to result in certain data with a certain privacy level now becoming part of the application, then we can assign a label to the application based on that. Yeah, so we haven't really thought about the fact that there could be malicious applications that are certainly trying to use this offloading framework. One thing we could do is we could say, all right, this application is requested to offload, and last time it sent a lot of execution state. And the computation it did was really small, which implies that we had a lot of overhead for very little benefit. And so we could deny future offloads from that particular mobile device and application to protect against something like a malicious application.